Hello friends, welcome to today's lecture, Stress and Strain. Myself, Mr. Y.S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Yadgaon. In this lecture, we studied about temperature stresses, linear strain, lateral strain, Poisson's ratio, and volumetric strain. In last lecture, we discussed about method of superimposition and stresses in composite material. So let us see temperature stresses. Basically, any material, if you heated, it will be expand or it will be contract due to rise in temperature or fall in temperature. Basically, due to this heating, the change in length occurs. Means change in length, due to that change in length is only produce strain. If you are preventing that the change in length, then the stresses will be produced in that material, and that stress is called as temperature stresses. The definition of this temperature stress is the change in length due to change in temperature is found to directly proportional to the length of the member and also change in temperature. Means basically this temperature stress depends upon length of the member and temperature in the or heating temperature. If the temperature rises, means due to rise in temperature, the length of the material is increased, means change in length is increased, and if temperature falls down, the length of the material is reduces or contraction occurs. Basically, this is the first A figure is free to expand, means due to rise in temperature, this change in length, that is B dash to B, this is a change in length delta L, and this is only due to that heating effect. If suppose this heating effect means I apply this P force opposite in the direction, means I preventing that the free expansion, then the stresses produced in the member, and that stress is called as temperature stresses. This is here, this is a figure C. Now this AB length as it is, and same time temperature T heating is going on. So due to that heating, the expansion will be occurs, but I apply this P force, or I am preventing this expansion by applying external force. Due to that external force the stresses will be produced, and that stresses called as temperature stresses. See the mathematical expression. Change in length, that is delta L, is equal to alpha T into L, where alpha is equal to coefficient of thermal expansion. It depends upon material. T is a temperature and L is a length of member. So basically we know that strain is equal to, that is E is equal to change in length upon original length, that is delta L by L. And we know the change in length, that is alpha T into L. Put up this instead of delta L, alpha T into L divided by length of the member is L. So L get cancelled. So we got strain is equal to alpha into T. And we know the equation that by using Hooke's law, that is Young's modulus E is equal to stress upon strain. So stress is equal to strain into Young's modulus E, and the strain value is alpha into T, and the Young's modulus E is capital E. So temperature stress is equal to alpha into T into E. This is the mathematical expression to calculate temperature stresses and temperature strain. Let us see one example. A steel rod of 15 meter long is at a temperature of 15 degrees Celsius. Find the free expansion of the length when temperature is raised to 65 degree. Find the temperature stress produced when the first condition is the expansion of the rod is prevented. Second, the rod is permitted to expand by 6 mm. Take alpha is equal to 12 into 10 raised to minus 6 per degree Celsius, and Young's modulus E is equal to 200 giganewton per mm square. So first, length of the rod is 15 meter and initial level temperature is 15 degrees Celsius, and final level is 65 degree Celsius. So we require to first find free expansion of the length. Means we want to calculate change in length for free expansion. So free expansion of the rod is L into alpha into temperature. Now in this case there is a two temperature. First one is a T1, that is 15 degree, that is initial level temperature, and second final temperature is 65 degree. So difference between these two temperature is our actual temperature. So T2 minus T1. So L is a 15 meter into alpha is 12 into 10 raised to minus 6, and temperature is 65 minus 15, that is T2, final temperature minus initial temperature. So free expansion of the rod is 0.009 meter or 9 mm. This free expansion is due to only heating. Then second one is the expansion of the rod is prevented. Means what? This here, this is, suppose this is a AB is a 15 meter length, and this delta L is now free expansion of the rod is 9 mm. So I want to restrict this free expansion 9 mm, means as it is I apply this P force at a point B. So the expansion is totally prevented. When expansion is fully prevented is find out the stresses. The temperature stress is equal to, that is alpha, means alpha into T into E, and this T is a difference between two temperature, that is T2 minus T1. So alpha is equal to 12 into 10 raised to minus 6 into 65 minus 15, that is final temperature minus initial temperature, into 200 into 10 raised to 3 Newton per mm square. So temperature stress when the expansion of the rod is totally prevented is 120 Newton per mm square. Then next, the rod is permitted to expand 6 mm, means basically previous expansion or that free expansion is a 9 mm. So we know that if the rod heated 15 degree to the 65 degree, the expansion will be occurs is 9 mm. Now out of that 9 mm, the 6 mm expansion is permitted, means only 3 mm is not permitted expansion. So find out stresses at that time. So when rod is permitted to expand 6 mm, in this case the amount of expansion to prevented is 9 minus 3, that is 6 mm, means we want to calculate stress for that 3 mm only. So strain is equal to expansion prevented divided by original length. So expansion is prevented is 3 mm and original length is 15 meter, that is 15,000 mm. So strain is equal to 0.002. And temperature stresses, we know the temperature stresses is strain into Young's modulus E. So strain value is 0.002 into 200 into 10 raised to 3. So stress is 40 Newton per mm square. See here difference between that point number 1 means determination 1 and determination 2. In determination 1, the total expansion is prevented, means totally 9 mm is prevented. So that time stress is 120 Newton per mm square. And in second case, the expansion is prevented only 3 mm. So temperature stress is reduces now, that is a 40 Newton per mm square. So stress is depends upon the expansion, how much expansion is prevented. If condition number 1, free expansion, in this condition if expansion is not prevented, then there is no stress developed in the member. Now linear strain, basically we know the strain value. Strain means change in length to the original length, and in this is regarding with respect to length. So when we apply, suppose this is a cross section, this is a member having cross section B and D. When we apply P force along the length, then this strain along the length is called as linear strain. The strain in the direction of the applied force is known as linear strain, and that strain value is equal to, that is E is equal to change in length by the original length. When we apply P force along the length, same time the length is increases, and same time the change in dimensions occurs. Change in dimension occurs means that B and D value will be changed. When you apply a tensile force, the length will be increases and simultaneously width and depth of the section is decreases due to that tensile force. So this B and D is a lateral strain. So lateral strain, the strain in the direction of the right angle normal to the normal action of the applied force as a lateral strain or secondary strain. Means change in width or change in depth divided by original width or original depth, that is the lateral strain. Lateral strain is equal to change in depth divided by original depth. Then next, Poisson's ratio. Within elastic limit, the ratio of lateral strain to linear strain is constant and it is known as Poisson's ratio. And Poisson's ratio is denoted by mu or 1 by m. Poisson's ratio is equal to lateral strain divided by linear strain. Then next, volumetric strain. When the body is subjected to forces in all directions, then it is the volume changes, and the change in volume per unit original volume is known as volumetric strain, and the volumetric strain denoted by EV. So EV is equal to change in volume upon original volume, and volumetric strain is the algebraic sum of all linear strain in the all direction, that is EV is equal to EX plus EY plus EZ. So let us see mathematical concept for this volumetric strain. First, concept about triaxial loading. Triaxial loading means, suppose this is a body having 6 faces and load applied on 3 direction, that is X direction, Y direction and Z direction. So this is a stress sigma X, sigma Y and sigma Z. In the X direction, sigma X on the right side as well as on the left side, sigma Y on this side and sigma Y on this side, sigma Z on the top side, sigma Z on the bottom side. So first calculate linear strain in the X direction. So for basically assume or basically consider X direction is a main direction or the primary direction. So due to that X, sigma X, the strain will be sigma X by E. Similar time, when you consider X direction, the Y and Z also applied forces or applied stresses on the body, and this Y and Z, now this is a lateral strain. So how to calculate lateral strain in the Y direction is sigma Y by E multiply by just mu. Mu is a Poisson's ratio, and consider minus sign because all forces are tensile forces. When you pull this X direction, Y and Z automatically reduces. So lateral strain in Y direction is minus mu into sigma Y by E. Next, lateral strain in the Z direction. Similarly, as per that sigma Y, minus mu sigma Z upon E. Once again I repeat, when you consider X direction, the X only linear, Y and Z will be lateral. So for Y and Z you multiply by mu and X consider as it is. So total strain in X direction is EX is equal to sigma X by E minus mu sigma Y by E minus mu sigma Z by E. Then next, consider in the Y direction. Now our main direction is Y. So linear strain is Y and now lateral will be X and Z. So linear strain is sigma Y by E and lateral strain in X direction is minus mu sigma X by E. Then lateral strain in Z direction is minus mu sigma Z by E. So total strain in Y direction is sigma Y by E minus mu sigma X by E minus mu sigma Z by E. Then next, in Z direction. Now our linear strain is in Z direction and lateral will be Y and X. So linear strain in Z direction is sigma Z by E. Then lateral strain in x direction is minus mu sigma x upon E. Then lateral strain in y direction is minus mu sigma y upon E. So total strain in z direction, that is Ez, is equal to sigma z by E minus mu sigma x by E minus mu sigma y by E. This is the total strain in z direction. So Ex is equal to sigma x by E minus mu sigma y by E minus mu sigma z by E. Ey is equal to sigma y by E minus mu sigma x by E minus mu sigma z by E. Ez is equal to sigma z by E minus mu sigma x by E minus mu sigma y by E. It is simple. When you consider x, the linear strain will be x and lateral is remaining 2, that is y and z. When you consider y, linear will be y, lateral will be x and z. When you consider z, linear will be z, lateral will be x and y. So calculate EV, volumetric strain, is equal to Ex plus Ey plus Ez. This is the value for Ex, Ey and Ez. Put up all values Ex, Ey and Ez. After this, solving this equation, we got EV is equal to sigma x plus sigma y plus sigma z upon E in bracket 1 minus 2 mu. This is the formula to calculate volumetric strain for triaxial loading. Means when you consider three direction loading, that is x, y, z, the volumetric strain will be this one. If sigma x, sigma y and sigma z are all three stresses will be same, then this formula is reduces, or the formula is right as 3 sigma upon E in bracket 1 minus 2 mu. Means similarly that sigma is equal to sigma x plus sigma x is equal to sigma y is equal to sigma z. Then when loading is biaxial loading means this z term is absent or only load applied on the x and y. So the formula is just remove this z term, that is sigma x and sigma y, means this is the linear, this is the lateral when you consider x, and when you consider y, this is the linear and this is the lateral. So equation is reduces, that is sigma x plus sigma y by E in bracket 1 minus 2 mu. This is the formula to calculate volumetric strain in biaxial loading. Then next, when you consider uniaxial loading means loading on the only one direction. EV, volumetric strain, is equal to, that is sigma x by E in bracket 1 minus 2 mu. This is the formula for triaxial loading, biaxial loading and uniaxial loading. In next lecture, we discuss about problems on volumetric strain. Thank you.